But anyway, so yeah, we've taken a nice step into the mathematics of dynamics, and just using these two models, interesting complex behaviors. But this is of course all modeling, right? So this is using models and just showing you what kind of stuff you can get just also using deterministic equations. But of course we don't usually have the luxury to know what the processes are that we're studying. So now we will move to more the analysis part of the course. So what happens if you have a time series and you want to figure out what's going on, what kind of dynamics are going on there. So these are some basic things that you can think about. But I'll start with explaining a little bit more about this concept of state space. But the main topic will be correlation functions. So suppose you have a system that is called the mini-me system. This actually stands for minimal memory system. And this is just a robot that is located somewhere in a bounded area, and it can move around. And basically what it's doing is, it's just receiving new coordinates to move in, and these coordinates are selected, I don't know, by a computer or something, and it moves around in this space, in this two-dimensional space. Yeah, it can move around within the boundary. So now the question is, if you look at its path, so it's the path it's taking around this space here, when would you infer that this thing is random? And when would you say, no, wait a minute, this is not random, there is really some rule going on here that is, something like we discussed before. So what kind of succession of states would make you think that this would be random, and what kind of trajectory? So let me give you two examples. Yeah. So which one would you say is random? Left or right? Or both or none is also optional.
Right.
Right? Yeah. So yeah, this is like a rock plot of the values that are on the x-axis. So the x-coordinate values. So you can see this looks, if you would make a distribution, this would be a normal distribution. So at least the values you see here look, for both axes, look to be drawn from the Gaussian distribution. And here it's not so clear, right? So these values here don't really look like maybe they're random, or maybe a little bit bounded here. But also if you think about the way we talked about this already, in terms of degrees of freedom, so suppose for this system, the degrees of freedom of the system to move around really are all the coordinates that are possible here. And this thing here, this pattern, appears to, if you wait long enough, it will probably fill up these edges as well, right? So this might look like a random kind of system. This is much more bounded, right? So this does not seem to be going to all the possible degrees of freedom the system has, all the possible states. Except Go. This is actually also produced by a random system. Actually, what I've been showing you is, so here you have the x and the y time series, and this creates this pattern here. So if you combine them, you get this pattern in 2D space. But what decides, the rule that decides to go from one value of x to the other value of x is just draw a random number. from the normal distribution. And those are these time series. So this is actually the time series of the increments there. And they are drawn from, at each point in time, they are drawn from the normal distribution and just added to the value that was already there. So if you take the cumulative sum of this, you'll end up with those time series. It's just adding up random increments. So it's a really random process, but not exactly random, because the thing you're doing here is you're combining them, right? You're combining x and y, and sort of constraining where the system can go, because it has to go where x says you have to go, and it has to go where y says you have to go. This is a constraint actually on the system. It's a very simple constraint. It's kind of an addition, kind of a counting constraint. But it is, if you think about real-world systems, so if this thing is really a robot, right, it has to move from one, has to occupy a point in space, and then it has to move in a random direction. The direction is randomly chosen, but the fact that it has to leave a point in space, that's actually what is causing this structure, right? This thing would be very difficult to imagine as a real system, because this would mean that the robot is here, and then it has to teleport to a random direction, and right. So in this case, you really don't have a memory for the system. So here you would have like zero memory, and you cannot predict where this robot will be going. It will be a completely random spot. But here you do have a very simple memory, and it's a memory of Lagg-1 actually. So you know where it came from. But at the next point, actually, you don't know anymore, because you cannot reconstruct it anymore, because it was a random choice for coordinates. Okay, so
derivative here means just change, and so the second derivative would be the change of change, but here the first derivative is just change from one point to the next.
Yeah. So if you want to, this is saying if I only look at the increment, so if I take the difference here of these values that are here, and you get this. So the increments are white ones, randomly chosen.
Okay. So just make sure the bottom right plot is just sequential numbers drawn from normal distribution.
Random.
Like you pick random coordinates and they are the next step, and then you do it again and do it again. And then on the upper right plot, these are added to previous coordinates.
Yes.
Is it the same as random walk process?
This is a random walk process. Yeah. So what you're looking at there is called a random walk, or I think Einstein called it originally a drunkard's walk.
There's a book by that name. It's quite nice.
Yeah. Yeah. So it is, and actually, so this was the topic of one of Einstein's 5 papers that he produced in 1905. And this model, so he came up with a model that describes this, is a model of Brownian motion. And this is not the color brown, but it's by Mr. Brown who first described this motion. He was looking through a telescope and he saw that dust particles in water tend to move like this. And Einstein provided the first mathematical model for this, and actually also gave us the sort of the conditions that are necessary, the assumptions that are necessary for this process to occur. But that's not where he had his Nobel Prize for, but still very important. There you go. This is a random walk, and it's called Brownian motion after Mr. Brown. And basically, what you do, it's taking the cumulative sum of random numbers. And what it was actually, it's still a pretty important paper, because it was a hint at that time. It was not actually known that there was such a thing as a molecule or an atom, because they could not actually observe those things. But this was one of the indications, or at least he assumed the existence of other particles in order to explain this behavior, because there's just the dust particle randomly bumping into things that you cannot see. and it turned out to be, I think that was officially established only like 5 years later, like 1910, 1913 or something. That was when everybody except Ernst Mach was convinced that atoms exist. Anyway, random walk. Where does this apparent order come from? Because it is actually, essentially, it's a random process. Yeah, well, it's just the fact that this is this system, or this if it's whether it's a particle or a robot or whatever you want, it has to occupy space. It's just a physical reason for this fact, and it has to leave that space to go somewhere else, right? So, and the other thing would be sort of teleportation, but not just that. You also would have to forget about where you were, and that's not a very realistic process, physical process. So this is also sometimes called, or this, I should say, this was further developed into a whole branch of mathematics that is studying diffusion processes. Right? So these are random, dynamical processes, time evolutionary processes that describe some parts of nature. Diffusion, for instance. But it turns out that diffusion is actually a very special case that you don't encounter very often. So anomalous diffusion is much more common, well, due to the sequence of historical discovery, anomalous diffusion came later. So this is kind of minimal form of physical memory, kind of natural computation. So structure emerges out of these temporal correlations, basically. There are different types of these motions. So this would be a random walk, which can be which is not self-avoiding, but there are also walks in which you try to not revisit previous coordinates. All right, and there are all kinds of different variations on this. The Levy flight is actually the same principle, but then you do not draw the increments from the Gaussian distribution, but from an exponential distribution. And Levy flights, for instance, are used to describe foraging behavior by animals. Percolation, that's the thing that goes on in your coffee machine if you use filter coffee. But very interestingly, the Levy flight model, the foraging model, is also very good at describing, for instance, eye movement patterns of visual search, or kind of memory type of tasks. And that's why they use these Levy flights also for. So this is again kind of a visual inspection using the return plot, right? So this is looking at the return plot. An interesting question might now be, this is a Lagg-1 return plot, so we already know for this one that if we go to look at Lagg 10 and 50 and 100, this will not change because it's random, right? But what happens to this one if we go to higher lags? Let's keep the suspense. Oh, yes. What? Change? Yeah. Yes. Yeah. There will something will change. Yes. Okay. Well, one way to use a more quantitative way to study this is to look at something called the autocorrelation function, or the partial autocorrelation function, or both even. And we can use ACF or PACF to write this down. And I mean, this is not really a difficult equation. I think it's actually the same as the correlation of how you would calculate the correlation, except you have now this I thing here, which is not the score of a different person, but the score of a different point in time, right? So you are comparing, so if I would be 1, the current point in time, with 1 plus some kind of lag, right? So if k would be 1, you would be getting the correlation of this cloud of points in the return plot of lag 1. But you can also have lag 2, lag 3, lag 4. So you can, for all these different lags, you can calculate the correlation that is then attached to a specific shift of your time series, and this you can plot this, and this would be then called the correlation function. So it's the average correlation between data points that are some lag apart in time. Of course, all the assumptions of the normal correlation apply here as well. So this represents the association only if there is really a linear association. But, and actually, yeah, you need random processing. But basically, the thing you should always do is just look at the cloud, right? What does it look like? Is it linear or is it completely different? And does my correlation mean anything? So looking at the autocorrelation function is usually a first step in time series analysis, especially the linear models, which we're not going to discuss. But the autocorrelation function is used to estimate some initial parameter settings for these models. So let's look at some of these things to get an idea what's going on. Suppose this is your time series. You have a time series of length 100, and you want to know what the Lagg-3 autocorrelation is. It means basically that you're going to create a data set which consists in one column of these points, let's say, and then the other ones are 3 time points separated. And then you just use the regular calculation for the correlation. So, well, how many we don't have to do these assignments, so we can just skip through them. It is of course the case that the longer the lag will be, you will calculate the correlation over less points, time points, so that can be a problem. But here you have like Lagg-3, Lagg-2, Lagg-1, they can still be done with these types of time series. And then you can figure out which you have a high or a low correlation at Lagg-3, for instance. Well, most of the times it will be going, when one is low, the other one will be high, and then when one is high, the other one will be low. So yeah, it will be pretty high. So the Lagg-3 correlation here will be actually almost 0.1. You take a little longer lag. Yeah, so there's just less time series you can use, right, to get this. What many software packages will do, I think SPSS also does this. It will just sort of assume that these things are symmetrical, so it will just continue again with the beginning of the time series, which is a little bit iffy if you ask me, but okay. Some software packages do this. Okay, so we have a lot less correlations sort of to compute. And I'm saying correlations, but this should of course be data points upon which you can calculate the correlation. So this would be pretty low. The correlation, probably because it's just it's not very consistent between the two data points. What is going on? Okay, so that's the idea. If you would use SPSS, you would find these kinds of graphs. I think they still look like this. So here are the lags in your time series, and this represents the strength of the correlation. So this is for the sine wave thing that I just showed you. And you can see that as the lag increases, the correlation drops. This would be the significance level. So the reason this is not a straight line is because you're using less and less points. So apparently you can sort of have settings in SPSS where it will take notice of the fact that you don't have an infinite time series. So in between here you would say these correlations are no longer significant, but then you get negative correlations that are significant. And then, yeah, well, this all becomes less significant because well, the time series is almost as long as the lag that you're considering. Okay, so this is what an autocorrelation function looks like. And here you would say this is a very highly correlated thing. So this is actually the sine wave, right? So this a very consistent pattern here. Very predictable. Yeah, so you might think about these different lags there as different time scales, right? So you're looking at a correlation between data points that are separated by an amount of time. So you could think about that there might be some frequency going on that is very specific. It could be at lag 3, lag 4 in this case, because it's this sine wave. That's not really a very accurate interpretation because it would just be the point where this would probably be the frequency of the sine. But yeah, you can sort of think about that, about the lags in terms of time scales. Yeah.
Is there you mentioned metaphors in your yesterday's lecture, the machine metaphor and the organism metaphor.
Yeah.
Have anybody used dramatic metaphors and theatrical metaphors while applying these dynamic models?
I don't know. What are you thinking about?
The autocorrelation reminds me of this concept of doppelganger. You know,
yeah. Yeah, well,
in dramatic dynamics.
Yeah. I can think of situations where that would apply. Yeah, but that maybe that's we'll get to talk about that when we're talking about fractals.
Okay, cool.
So usually you don't look at like 100, so you need to look at the number of lags that make a little bit sense. And then it would look like this.
What do you mean make sense?
Yeah, I mean, so if you have a time series that is 100 data points long, yeah, why look at lag 100? I mean, that you don't have enough time points to get an accurate estimate there. But lag 20 will still give you, yeah, some data points to calculate this correlation on. All right, so that's just.
So how do you decide upon what's enough?
There are of course guidelines. You know, how many data points do you need to calculate a correlation? The same rules apply there. Yeah. So this was our autocorrelation function going up to Lagg-3. This is the partial autocorrelation function. I don't know if you know about partial correlations, but the idea is that you want to account for the fact that you already know something about an association between other variables, for instance. So you can partial out what you already know. And in the case of the autocorrelation, what happens here is, so at lag 2 it's also pretty high, but we're saying now, yeah, but we already know that lag 1 was even higher, right? So what if we take out the fact that we know that at lag 1 there's this really high correlation? What is left then? What is left? What is unique about lag 2 in the very linear sense? And then you get something like this. So in this case, you have here the same lag 1 autocorrelation that's pretty high, and then apparently at lag 2, 3, you just have some negative contribution. So that's actually saying, if you want to understand what the correlation is at lag 2, you actually have to know that it's a little bit smaller than at lag 1. right? It's kind of the same here. But so the partial autocorrelation represents, yeah, the independent contribution or independent correlation at each lag. And this is this is very often used to get an idea about how many autoregressive components you need in a model if you would go about those things. But now let's get back to our system. Yeah. If you look at so we had these time series, right? X and Y, and this was the state space. So let's look at X. So this is the autocorrelation function of X. You can see that it takes a very long time before this correlation drops. So at lag, I don't know, over 200, there it becomes non-significant, which means, which could mean that it's a highly deterministic system, right? So correlations everywhere. But if you look at the partial autocorrelation function, you can see, well, that's a mistake to think that, because there is just one correlation, and it's at lag 1, and it's actually 1. So it's a correlation of 1 at lag 1. And that's actually the summation that you're doing, right? So that's the cumulative sum that you took. That's represented here. So the only memory that is in the system exists actually at lag 1. So you know where you came from, but if you go one step further, that's again in random direction, and you really don't know anything else, basically. So if you then look at the time series of the increments themselves, right, which was white noise. White noise, if you look at the autocorrelation function, has a correlation of 1 at lag 0. So the only information you have about white noise is that the same value at the same time point is correlated with itself at 1. Right? So that's the definition of randomness. That's the definition of white noise. There is no other information you can get out of it to predict what is going on because it's absolutely random. And then, of course, in the partial autocorrelation function, there's nothing. And so if you see this, you know it's truly a random time series. And if you see this, you might at first think, wow, this is a complex thing because there's lags, there's values are correlated across huge amount of time. But actually, if you look at the partial, it's all you can sort of understand what's going on there just by having a memory of 1, basically. Yeah, so that's sort of what I just said. So it's always good to look at both of them, right? So autocorrelation as well as partial autocorrelation. Yeah, so one of the techniques that are often used to figure out whether you're dealing with something that's random or not, which is often, by the way, one of the important questions in time series analysis. So how much of a deterministic system do I have? Is to use, we call it surrogate analysis, and the simplest form of surrogate analysis is to just randomize the order at which you observe the time series. So destroying the correlations basically with the data. So the autocorrelation function of this is a sine wave with some random noise added to it. Yeah, this looks like there are some interesting correlations going on. So if you just randomize it, you get something like this, and then it's really white noise. Right? So this is an extreme example, but there are situations in which it's not very obvious what will happen if you destroy the temporal order of the observations. But so that's called surrogate analysis or shuffling the data. And what you would expect that if you randomize it, if you shuffle the data, well, then you should have destroyed all the correlations that are in there. And maybe, yeah, I think we'll talk about this tomorrow some more. because there are more sophisticated ways to do this. Oh yeah, no, this, and of course the same will happen with the partial autocorrelation function, right? So that should also then tell you that there is zero correlations after shuffling. Yeah, this is just to show you that we're not going to discuss this. So so the linear time series models that are called often autoregressive models, so ARMA, ARIMA, and all kinds of extensions of these models. So what they do is, if you have a time series, they ask you to look at the autocorrelation and the partial autocorrelation, and then they have all these very complex decision trees that should help you. So you need to look at the shape of the autocorrelation function, and then you should decide this and that, and then do this, and I don't know. It's sort of becoming a kind of an art form, and it's not always obvious for me why certain choices are made. So let's just not do that, because one of the reasons is, of course, also that the time series that we are getting, that we are looking at, already do not conform to the assumptions that are necessary for these models. So, for example, if you have a non-stationary mean, that's a problem. So these models cannot deal with that. If you have unequal variance, so there might be a period after which the variance increases or decreases, that's a problem for these models. If you have sudden jumps, that's a problem. If you have differences in periodicity, it's also a problem. And these are the kind of things that we know, not as stylized as here, but that's actually the kind of stuff that you encounter if you're looking at real-world time series. So you can actually test for these things. I did not discuss what ergodicity is. I did discuss it yesterday, but well, the very simple definition is if your time series is stationary, and if the variance or some other central moments are homogeneous, then you have ergodicity, and then you can do your regular statistics. So for time series data, there are a lot of tests that have been developed that you can apply to your time series and figure out whether you actually are whether you have stationary and homogeneous time series. This is a link to a blog post in which I try out some of these assumptions, but you can do a little bit better because we are now writing a paper in which we are actually applying this. So I'll show you some of the results. This is from a study called Critical Slowing Down as a Personalized Early Warning Signal for Depression. This is a case study, so this is one person. And these are all variables. And they've been measured for over 238 days. Yeah. So this is a multivariate time series data set. And there are all kinds of questions in there. So, did you feel alone? Are you sleepy? Are you dizzy? How was your? Are you feeling relaxed or satisfied or strong? And this was actually an experiment. So, this person, who is also the second author of the paper, was taking medication for depression, and so it's a double-blind experiment in which he and his doctor did not know at which point the dosage of his antidepressant was lowered. Yeah, so there's a baseline period, and then there's the experimental period, and then they don't know at which point they start lowering the dosage. And what you see here is the symptom severity of the depression scale. And then, you can see, so this is the onset of the period, and then you can see there are these jumps, these peaks in the symptom severity. And then here, this red point here, there's actually no data here because they decided to stop the experiment because it was getting too much. And then they restored the normal dosage, but you can see that something happened, which is not very pleasant for the subject, because yeah, he really got into a depressed state again. Okay, so the goal of this this article was to figure out if they could predict whether this thing was coming, but I'm now using it for a different purpose, because what I want to know is, and what they used to assess these things were techniques that actually assume that those time series are stationary and homogeneous. Right? So what we wanted to show or figure out is that really the case? So what you see here is, so these are the names of these time series here, and these are all different tests that you can do for stationarity and homogeneity, and so there's something called level stationarity, which tells you if there's no shift in the mean level. But if there is a shift in the mean level and it's and that shift is actually stationary, which just means there's a slope which is linear, you know, that's maybe kind of okay, because then you can detrend the data. But there's also a test for that, so you can test level stationarity and trend stationarity. So trend stationarity would be testing we have the same slope everywhere.
What does unit root mean?
Sorry?
What does unit root mean?
Yeah, yeah, that's the way the test works. So this is one of them, but there are many different variations of it. And I think it has to do with, I have to look it up how it is exactly, because otherwise I'm saying nonsense on camera. It's not good. So, but the thing is, without going into the details, the fact that you're seeing these things turn up significant here means that most of these things are actually not stationary, not homogeneous, and they violate the assumptions behind the statistical models that were used in this study. Except for some, and that's maybe interesting. So, for instance, I feel dizzy, I am hungry, I feel nauseous, I have a headache. These actually are quite okay. So you could consider those as kind of random. But if you think about, for instance, I am hungry, so the way this was set up is at several points during the day you would get a question, and those points were random, right? So they were randomly chosen. So if I ask you at random at one point, are you hungry? Then yeah, you could be hungry, that's fine. But the next day could be after you've eaten and you're not hungry anymore. So if this would have been sampled like every hour, it would probably have turned out to be very, maybe sinusoid or something like that. But just because it's sampled right, not at the frequency at which this process is changing in a kind of, well, maybe periodic way, it turns out it looks just like a random time series. Yeah. So and this part here, this is where we looked at the autocorrelations data. And we just noted the significant, so the partial autocorrelation function, and at which lag do we still have, no, that's not true. How many significant partial autocorrelations are there? Not specifically at which lag, but these are at lags 2 to 99 and these 100 to 1000. And you can see that if this would have been some kind of random process, these kinds of things, this should all be 0. I mean, you don't expect at lags of 100 to 1000 to be 11 significant partial autocorrelations. Right, so what the dynamics that are going on in these series that are actually all about psychological variables, not physiological, but these are psychological variables. Indecisive, cheerful, guilty, anxious, lonely. The dynamics there are much more complex than anything you could model with a random-like system. And which makes sense. So for instance, whether you are when you're asked at a random point in time whether you're hungry, it actually doesn't depend on what you answered last day, because that was asked also at a random time. So those things are probably not correlated. But if you have to say I feel down, yeah, if you've been feeling down all week, it's probably likely that you will also answer I feel down at this point. So those psychological variables are really different things than the more physiological variables. And you can see this here. So this is the autocorrelation function for I feel down, and this is the partial ACF, and you see there are all kinds of significant correlations going on. They may not be very high, but it's at some point significant. And this is partial. This is partial autocorrelation. I feel hungry, almost nothing. Right? There are some here, but this looks much more like this white noise partial autocorrelation function than this one.
So for autocorrelation functions, do you have the same thing as with correlations normally, that you would have to do some kind of multiple testing correction, or how does it work in that sense?
Yeah, if you want to know these significance bounds, yeah, I think that it really depends on the kind of technique that's used, but it could be that if you see these straight lines, I think they will assume that those different lags are independent, right? And actually observing a correlation at those lags would kind of violate that assumption, I guess. But another, I think they also do bootstrapping to get these bounds. I think that's what I do in R. I'm not sure. I think I do bootstrapping. But anyway, if that's really what you're interested in, and so in deciding whether it's significant or not, I would suggest that you should do some kind of correction. And then, of course, it might be that those things also will not be significant. But well, these up until 4 or 5 probably will. So that's and in terms of partial autocorrelation, that is still something, right? That's still pretty complex. Okay, that's the autocorrelation.